We are going to today start, although the period session is a little bit too short, but we are going to start, I should say, it's kind of thing that for example, you have the chips, you want to dip it to see how the dip tastes. That's sort of what we are going to do today, something like that. You have the chips, you want to dip it to see, that's the new concept, that's if I like the taste or not. And now, the concept is going to be the concept of the optimization. We today spent maybe around half an hour to, as I said, do a little bit to see how it is. Then when we come back next session, we are just going to work more on some more important problems. Now, today we are going to develop some strategies essentially when it comes to the optimization. Okay, before we start, I'm going to remind you of some of the very important things that we covered that, I should say, before we go for the November debrief. And essentially those things was around this, was revolving around these concepts. That we said that we have a function which is a single variable function, because the thing that we're going to cover today, it's called optimization. There you can just go for a PhD, spend 6 years in math to look into the optimization techniques. That's a huge discipline. Honestly, you can do a PhD in math focusing on the optimization. Today we are going to start optimizing a single variable function, because when you just go to university, you are going to be given functions which they have more than one variable. Then the optimization becomes so fun. Then it becomes so interesting. But now, when we have one single variable, we are just going to have an easier job to do that. Now, what is the strategy? I'm just going to first of all remind you of the things that we did before we go for the November break. We thought that, for example, we said that if we have a function which is f of x, it's a single variable, which means that you can just visualize it into, I should say, the xy plane. And imagine that's going to be the function f of x. And we also learned that, if you remember from the previous session, that always we are looking to restrict ourselves into some kind of a domain or intervals, which I'm going to call that from A to B. We said that if we are constrained to just visualize that functions between the interval, which is A to B, we can just come to a kind of an algorithm to find the points which are going to be the optimal ones in that interval. Either you're just going to stand at the top, or they're just going to be at the bottom of that function. Oh, yeah, please. That's what we said. We said that, okay, how to find these 2 points? For example, I said that within this interval, I may say that these points, which I have here, it's going to be my minimum point. And in order to find that minimum point, or let's say, for example, I say that this point, around this point, if that's going to be the maximum point, if it just is still within that interval. We said that we can find these 2 points by using some concepts that we have learned within the context of the derivatives. We are lucky so far that we have learned the rules of the differentiation. Now we can tackle these ones. We said that we have some strategies. Step number 1 was that we said that we find the first derivative of that function, which means that we find what is d over dx of f of x. It was step number 1. First of all, you want to just see what is the mean or max. You are looking for the optimal points. You close your eyes, find the first derivative of that function, provided the function that you have is continuous along the AB interval. That's a very key criteria. Now, the second step that we developed before we just go for November the break was that we were supposed to find this equation that the first derivative has to become 0. And now, what we said that, okay, then we say that d over dx of f of x becomes 0. We solved this equation. And as a result, we said that, okay, we can find the roots, the zeros of that function. From this, as a next step, we said that we developed we looked at the sharp changes of the tangent line around x naught. What is x naught? It was this one. D over dx of f of x naught becomes 0. So much words. Let me explain what did I write. We found the zeros of that first derivative, and I called it f of x naught. I called those zeros x naught. Then, if you remember, we said that we are looking for the sharp changes of the tangent. What did I mean? For example, we said that the tangent around this point is now negative. Now, after it becomes 0, because the slope is 0 at the minimum point, then suddenly becomes positive. And if you remember, we showed this step by using, for example, a line, for example, a table. We said that this is f prime of the x. We noticed that it has a 0 there. And we said that, for example, if between the interval, for example, we have increasing, let me show that this way, that's what we do. We have increasing the slope. Then we have decreasing the slope. We said that this point becomes what? Like this, look at that. Now we have decreasing the slope. It changes to become increasing the slope. It becomes what? Now this is the reverse. It becomes maximum. And also, we developed a fourth step strategy, and we said that the second derivative test what was that method? It was a kind of a strategy that we use it to make sure that the points that you got over here, it's not, for example, a wrong guess. For example, you say, it's maximum or minimum. Let's do the second test. What was that? We said that we find this expression, the second derivative, which is d2 dx squared of f of x, which is the second derivative. And what was the test? If you remember, we said that the result of the test is this. If the second derivative of the point that you got to be the max or minimum, you substitute x naught, the zeros of the first derivative, into your second derivative. If it becomes positive, it means that the function is concaving up, which means that then your x naught is minimum. But however, if you do the second derivative test with the zeros of your first derivative and it becomes negative, what we said that, okay, that point, then because negative, is concaving down, and that point becomes my maximum point. And that's essentially the summary of all the things that we do before we just go for November the break. The second derivative test was a kind of a thing that you check your work at third step. It's an easy one. Get the second derivative, put the zeros of the first derivative, either becomes negative or positive. Depending on a sign, it shows that, okay, this point step number 3 was maximum or minimum. And sometimes you see that you do not even need to just go number 3. You can right away go to the second derivative test, put the zeros there into the second derivative, if that point is maximum or minimum. But you have to be careful, that's not always true. Then I advise you always do the third step before going to the fourth step. Now, any questions on this so far? Go? Yes. Now, this is actually a kind of a review of finding the max mean of an arbitrary function f of x. Here's where the algorithm we developed to solve the max mean problem before we go to the, it's kind of review, refresher. Okay. Now, and that's a good question, Tommy, because now I'm just going to follow you and continue with the new topic. The new topic is optimization, and essentially this topic is exactly the same thing that we solved for the max mean problem. Because what do we mean that we want to optimize something? For example, now I teach here, they give me, for example, some kind of a salary per month. I'm not happy with that. I want to optimize it, increase it. That's right. Or I spent too much on coffee. I want to optimize it. It means that I'm just going to spend less to minimize the expenditure which I have on my coffee. Now, when it comes to the optimization, then we are going to use this over a context. I give you a problem. Then, for example, I tell you, for example, if x represents the number of the coffee which I take per day, and this function what is the most minimum, I should say, the least cup of coffee I can take per day that still I'm awake? Then you see, oh, you see this is still a function, this is still f of x. I'm looking for something as a minimum, then I have to follow these strategies. Then as a result, the optimization problem is all the things that we have learned, but it has a context with it. Now, what do I mean? I'm just going to solve one example here. I'm writing from here, and I'm the We're just going to start by something which is somehow, it's a very popular type of question. It comes always on the exam, on the test. You see it everywhere. I say that, okay, I'm going to look at this. I have a piece of paper. Maybe you have seen that example from level 3. It's a very popular type of questions from level 3 and level 4. We say that, okay, I have a paper, for example. It has dimensions, which is the length and width. I assume that both sides, the length and the width, is given to me, and I assume that this is 24 centimeters. Now, you say that, okay, I'm just going to make an open box with it. By open box, what do I have to do? I have to bring the scissor, cut these small areas which they are equal from all four corners of that paper. You have seen that problem before, huh? From level 3 all the way here. Now, that's the purpose which I use this question is that now you can see that this has become an optimization problem, and I'm going to solve it using these 4 methods. Now, I say that if I just want to just cut these corners from this rectangle paper which I have, I'm just going to, first of all, what do I need? We say that for the optimization problem, definitely I'm looking for the function first, because that's what I did here. I had a function first before finding the maximum or minimum. Then the thing which is remains for me is that I express, and the question which I have, my bad. What is my question? What is my objective? Is that I'm going to ask you guys, for example, I just give that paper to every one of you, and I say that paper dimension is 24 by 24 centimeters. I give it to you with a scissor, and I say that cut these corners in a way that you get the maximum volume possible. How much is that going to be? You say, oh, I have a scissor, I have a paper. How much should I cut from all 4 corners to get the maximum volume possible? You see? Was it me? Oh, no problem. Like you see that, okay, yes.
Are we trying to find the area?
That's it. We
So
just
the
want to
area
find the volume.
of the corners or of the shape?
No, of the shape. You cut these ones out, you fold it from the four sides, then you make a box. Then you want to find the maximum volume. Look at this, for example. This paper, I'm going to cut this four area.
Okay.
Then I fold these times like this to make a box from it.
Oh.
And the volume of the box, I want to maximize it.
Oh.
Become the maximum, the biggest box. Does it make sense?
Yes.
Awesome. Now, you see that the problem which you have from level 3 now it is expressed in terms of the optimization problem. Now, then the question is how much is going to be maximum volume? Look at this, maximum. That's why it becomes optimization. The starting point in my algorithm is this, to express the volume as a kind of a function. If this is V, I'm looking for a kind of a variable which I can find a function as a single variable. What if I say this length becomes x, and also this one also becomes x, and all of them the same, they are equal? Then what is the volume? I know that if I cut x from here, this dimension becomes how much? 24 minus 1x from here, and 1x from there becomes 2x. For this side, and also the same thing here. I know that this is also x. This is also x. This is also x. This one is also x. Then also, the other length is going to be 24 minus 2x. Right? So far, so good? How much time do you have? Now, and if you look at this, if you fold it from these corners, this length is this length is this, what is the height of your box? X. Then also you have to multiply that to x. Then you have what? You have, let's say, if I can draw it correctly, then you see that this box, this length becomes 24 minus 2x. This length is 24 minus 2x. And this length becomes x, which is the height. Now, that's the volume. This represents the function which I'm trying to optimize it. Okay. Now, at this stage, it was a very important. Look at the view that. Sorry for distraction. I couldn't say nothing. Oh, look at that. Now, I couldn't help myself. Now, this step was a very important one because at this step, I constructed a single variable function. And always remember, when you just go to your handout, you see that on your test. You work in a company, you just want to optimize, for example, the revenue or minimize the cost. Always you have to start with something which models the problem that you're looking for. And that essentially models the volume of this open box. Step number 1 in optimization. Model the problem that you're looking to optimize it. And that's my model. Now, from here, normally the most problem is this, how to model the problem. This is the bigger part. When you are done, you come back all the way to here. You follow these 4 steps to optimize it. Now I'm going to do this. Then please follow me step by step in order to maximize the volume of this open box. Step number 1. Yes, I'm speaking now. Now, what I'm going to do is that I'm going to find the first derivative of the volume. What is that going to be? Well, you say no problem. We have learned it before. How to do this? Look at that. There are three functions. You look at the product rule, and what do I say is that the derivative of the first functions times the rest. So it becomes minus 2 times 24 minus 2x times x. Plus the derivative of the second function times the rest. Again, the same thing. This is minus 2 times 24 minus 2x times x plus the derivative of this function times the rest, which is 24 minus 2x. I put it to the power 2. That's what we have learned so far. I use the product rule to just find the derivative of this function. Now, let's switch around with them to see that if I can simplify that further. I have this one here, then it becomes what? Becomes minus 2 times, becomes minus 4 times 24 minus 2x. Look at these two terms, they are similar, plus 24 minus 2x to the power 2. This is dv over dx dv of x. This is the derivative of this one. Yes, do you have a question after that? No? Any questions, guys, so far? I didn't do any crazy thing except I used. How much time did you have? 25 minutes, huh? 10 minutes.
15.
15.
I have a question.
Yes.
So I understand that we found the derivative of the function that equals the volume of the box. Does this really go in context? What does this derivative of the box?
Oh, still nothing. Now we are moving back to abstract math. Still doesn't mean anything. Now, look at this. Is now I have this one. Let me expand everything. Guys, please someone use a calculator to expand this. 24 to the power 2. How much do you get? 576 minus 2 times 24 times 2, 48 times 2 becomes 96. Am I right?
Yeah. Minus 9.
Yeah.
Minus 96 x plus 4x squared. I have this one minus 4 times 24. How much do we get? 96 minus 90 minus 96 times x plus 8x. Am I right? Minus 96 plus 8 x squared. Thank you. Which means that v over dx of v of x becomes 12x squared.
Where'd the 576 go?
Here, I'm going to add it. I have minus 96. Minus 96. How much do I get?
Keep with the order so that you
Becomes 100. Can you get out? 96 plus 96. 196. Minus, thank you. Plus 576.
Okay. Yeah, okay. Wait. No,
Guys, we do not have much time, just only 10. Yes.
Where did the 576 go?
Still, this is here.
Oh, so
I added them together.
so that's the same equation you
That's
put
right.
on two lines?
Plus, that's right. Plus comes here.
Oh, okay.
Yes. Now, guys, step number 1. How much? I think we do not have much time. Let's speed up. Step number 1 is done. I took the derivative, Sebastian.
Yeah.
Now, what I'm going to do, I'm going to solve it as an equation. It becomes step number 2. I say that d over x of v of x becomes 0. Let's change the colors to all flash. Now, what does it mean? It means that now I have 12x squared minus 192x plus 506 becomes 0. Now, go back to the level 3. Now the task is this, how to solve this. I'm going to divide both sides by 12. How much do I get? X squared minus how much do we get? 192 divided by 12 is 16. Minus 16x. And if you please do that, so 506 divided by 12 plus 28 equal to 0. Now, guys, look at this. Do now.
Yes.
Look at this, everyone. Now, we completed the step number 2, which was solving the first derivative equation, and we find the zeros of it. Now, we are going to find the zeros of that equation. Still on step number 2. In order to solve this, how am I going to do? I say that I'm looking for two, it's very easy, level 3 math. I say that I'm looking for two numbers, that their product is 48, their summation is minus 16. What are those numbers? 4 and 14, huh? 4, 12.
12.
That's right, x minus 4 times x minus 12 becomes 0. Now, it's easy to solve it now. 1x has to be 4. The other x has to be plus 12. Now, okay, now we solve this. Step number 2, we got the first derivative, we got the zeros of that. One of them is 4, the other one is 12. What was actually the x, Cyrus? X was essentially the part that we cut from the box. Now we just want to use the x in order to find the maximum value. But wait a minute, guys, look at this one. I have two answers, and I also, everyone look at here. Please do not write anything, just look at them. And now here is that the optimization problem always comes, this part, this sentence which I'm going to tell you, it is very important. All the optimization problem that you're going to solve always comes with a restriction. What does it mean? For example, you say that I just want to maximize my, for example, the output from the factory, but I have a problem, I don't have enough money to buy new materials. They say that, for example, that becomes your restriction. Now, in this context, I got two solutions. One of them is, guys, please listen. This is very important. I got two solutions, 12 and 4. I come back to the same thing which I got. I noticed that if I put 12 here, I got 24 minus 2 times 12, which becomes 24 minus 24, becomes 0. Then it becomes 0 times 12 becomes 0. What is becoming 0? My volume of the box. Are you looking for something that to have a volume of 0 the box? Now, it means that you crumble the paper and put it in the garbage if the volume is 0. You are not looking for this. Then you say, okay, this answer which I got from here, it cannot be acceptable because it gives the volume to be 0. And that's where your restriction, Leon and Sebastian. You say that, then if I put 12 there, then the volume becomes 0. Then you start to think, oh, okay, the restriction which I'm going to impose into my problem is this. First of all, x has to be positive. It's obvious. X is the length. Length cannot be negative. And at the same time, x cannot be 12. That's the restriction that we impose on your optimization problem. Then from now on, any problem that you solve on optimization, you have to be always watchful for the restrictions that you have to impose. Yes?
For this though, if you do, like, if you check which one's the maximum, technically 12 is minimum. So just like
12 is not minimum. 12 is a problem. Because if you put the 12 there, the volume crashes to 0.
for this function, 12 would be minimum. So you would just disregard it anyway.
We'll just disregard it because the volume cannot be 0. That's a red zone for us.
Okay.
Because if you put 12 there, it becomes 0, then the box volume of the box becomes 0. It means that you crumble the paper, and it doesn't make sense. Always some of the answers becomes a restriction. Okay, but that's a good question. We can have a minimum, but here it's a nonsense minimum.
You don't need it.
It's a new word that invented, nonsense minimum.
I have a question.
Yes.
Is it x can equal 12 or x has to be smaller than 12?
No, it cannot be 12.
Well, what if it's
But we cannot have small up. That's a good question.
it can't be
It cannot be, guys. Listen, we are going to finish in 2 minutes. It cannot be even smaller than 12. Why? Because in our optimization problem, what was our strategy to solve this equation? Our answer is the root of the second derivative function. What is the root? Either 4 or 12. We notice 12 is impossible. Then it can be specifically 4. Because 4 is the only root of step number 2. If step number 2 doesn't give you range, that's not an equality, that's an equation. Then only 4 is the acceptable answer. And for 12, you have to disregard it. Does it make sense?
Yeah.
Awesome. Now, the last step. We do not do this step because it doesn't make sense. You can do it yourself, but we skip this. We have only one choice, and we take it as the point that we are looking for. I'm going to step number 4, the second derivative test, to see that if the thing which I got over here is the answer for me. What does it mean? It means that I have to get, I'm just going to erase this. It means that I'm going to get the second derivative. What is the second derivative? I look at the first derivative, take the derivative of it. It becomes 24x minus 192. Now, second derivative test, it says that you take the zeros that you got, which is 4, put it in there. It becomes d over dx squared of the v of x equal to 4, which is 24 times 4 minus 192. How much is that? It's anything, but that's for sure is a negative number. And what did we say? That we said that if we get the second derivative and put the zeros of your first derivative into that, and it becomes negative, it means that the x that you got represents the maximum point. Which it brings us back to this point that x equal to 4, which you can say centimeter, because this is the length of this part. It means that if you cut only 4 centimeters from both sides, you have a box which the volume inside is maximum. Isn't that beautiful? Yes, Leon? What? Now, essentially, guys, congratulations. You learned the first problem in the optimization field. Then you see that the starting point is always to model your problem, then use 4 strategies. Yes? Makes sense? Yes, yes, yes. Oh, makes sense. Glad to hear. Oh, you optimize the problem. Isn't that good? How much time do you have?
Oh, it has to be.
We have 5 minutes.
That line is